being here. My talk is going to be about some joint work with Salma Kuhlman from Constance and Bernard Morin from the INRIA Côte d'Azur. So the topic is mainly these kind of symmetric tensor decomposition problems. We heard about them yesterday as well during Darius' talk, for example. These are some kind of additive decompositions where you take a symmetric tensor, which this talk is just going to be, as we saw, just a homogeneous polynomial, and you want to write it down as a finite sum of some powers of linear forms. And this, what I'm going to try to sell to you today is that this problem is quite a complicated one, but at the same time very important. Yeah, we've seen some connections of this problem, for example, with the moment problem, as hopefully you heard yesterday during Yassin's talk. And I will focus specifically on these kind of Warring decompositions. So you fix a variety. In my case, it's going to be a rational variety with some extra hypothesis on it. And you want to see whether a symmetric tensor has a Warring decomposition on this variety. So this is what Darius yesterday called like X rank. In his notation, V was X, but that's the same thing for the Warring decompositions. What I'm going to do is I'm going to answer the question, but we need an additional assumption.
Sorry.
Yes.
Your X.
Yes.
Because you said it's the same as the X rank.
Yes.
So
I think so.
The case of Dario was that X was our elements in Pn, and then it was free to choose lambda and then times something. And that something was a variable. But your case is slightly different, right? Because you're choosing the x's to be somewhere else.
X is the Veronese.
Oh, sorry.
Yeah, it's not the same, right? That's what I'm saying.
Sorry. What am I doing with the presentation? I'm sorry. So
let's understand starting point. So your x's are where?
No, so the x's here are variables, and the points on the varieties are the vi's. Perhaps I misunderstood Darius.
Yeah, I think it's exactly the same thing, because Darius' thing was the sum of lambda and then some, let's say, some p that belongs to some variety.
Okay.
You're doing exactly the same thing. You're doing a re-embedding of
the variety with the Veronese embedding. Yes, exactly. Okay.
It's very similar, but it's not exactly.
Okay. Thank you very much. Sorry. Okay, so let me introduce quickly some notation. We're gonna work either over the real numbers or over the complex numbers. This does make a difference when we speak about the compositions, because if you take a larger field, then you have more freedom and can get maybe shorter decompositions. This curly S is gonna be the gradient algebra of homogeneous polynomials, and when you see the star, there is going to be just the algebraic dual of this space. With bold symbols, I will indicate tuples. So tuples of variables, numbers, forms. You get it. And with this capital M, this is just a set of monomial like exponents, okay, of some fixed degree and number of variables. Finally, I want to introduce this polar inner product, which is the one you see at the bottom. It's just a very convenient inner product that we endow our space of forms in some degree and some number of variables, which is going to be quite convenient. And with this polar inner product, we get this map between the vector space of forms and its dual, which is an isomorphism. And again, finally, T is going to be just the transpose of a map, and then we have the adjoint whenever our vector spaces have some inner product. Now, let me define properly what I mean by Warring decomposition. You have the symmetric tensor, and you want to find a natural number and some weights, these lambdas, and then the points where the Warring decomposition has the support. And we want them to be distinct in the projective space. Otherwise, you could collapse two summands into one. That's just why I am adding this restriction. Now I'm gonna quickly define a space, a vector space inside the space of forms, and then I will tell you why this is important. This map WQ is going to be important throughout the talk. This is just taken in the space of forms here, where that in n+1 variables I will then apply x, and n+1 variables by z. This is just a substitution plus a multiplication. So we substitute the variables xi here by the forms qi, and then we just multiply it so they react on monomials, and then you get a linear map on the whole space. Okay, so this is just a simple map. And now, given this WQ, what I'm really after is this composition that looks somewhat abstract. So let's take a look at it step by step. So we start from the codomain of WQ. We use the polarity map to go to the dual. Then we have we use the transpose of WQ, and finally apply the inverse of the polarity map again. So we get a map going in the opposite direction as WQ. And whatever this monstrosity is, I'm gonna define a vector subspace, which is the image of this map, and this is what I'll be calling q-symmetric forms. And I'm telling you that this is the object that we are interested in, for the following reasons. First of all, note that whenever this phi is injective, then we can easily obtain a basis of the q-symmetric forms just by taking the image of a basis in the domain, your favorite basis, like the monomial one. So it's quite easy to see what these polynomials look like. And in particular, it is proved that, for example, this phi is just the adjoint of WQ with respect to the inner products. And just to not make them so abstract, you can impose this hypothesis of surjectivity on WQ so that phi is injective and get a basis. So we just see them quite easily what they look like. And even though this may be ugly, this is just some multinomial coefficients, and this is the entries of the matrix of WQ with respect to the monomial basis. So it is we can easily see what these polynomials look like. And finally, I just want to remark that if we restrict phi to the image, we can get a nice isomorphism between the q-symmetric forms and these symmetric tensors in the domain in the variables z. So these q-symmetric forms live in the space where we have the x variables, but at the same time they encode the information of some other forms in a different number of variables and a different degree. Whatever this means and how this is going to help us is going to be clear now. But first of all, let's see a quick example. So we fix some forms Q. Trust me on the fact that with this choice, WQ is going to be surjective, so everything works fine. And we can, for example, just write down a q-symmetric form. So that this is not difficult to do at all. Even though the definition is quite abstract, it is not so tough to visualize these forms. So we start from a polynomial in the z variables and then send it through through phi, and this is the q-symmetric form that we get. Okay. Now let me introduce the concept of these q-symmetric decompositions, which is exactly the object of this talk. A q-symmetric decomposition for me is going to be a Warring decomposition, but you see that the nodes now are different. The nodes are exactly evaluations of this tuple of Q in some point. Other than that, we don't get any other difference. So these are exactly the decompositions, the Warring decompositions on the variety, which is parameterized by the tuple Q. So VQ is going to denote the variety, given by the closure of the image of this map. And you see that depending on Q, this may be somewhat of a problematic definition, just simply because maybe the Q vanish all at the same time. So this is a rational mapping. Okay, let's go to the main result. If we assume that WQ is surjective, then for any q-symmetric form, we can have this correspondence between q-symmetric decompositions. So again, Warring decompositions on the variety and Warring decomposition, like standard Warring decomposition of the associated form in the space of Z variables. So there's this correspondence which also preserves the length and lets us understand how one can find these decompositions over the variety V. As a corollary of this result, we also get that the q-symmetric forms are exactly the forms that they were in the composition on this variety. So we know exactly who these symmetric tensors are. This is just a matter of once you choose your favorite q, doing some linear algebra. Unfortunately, we gotta address the elephant in the room, which is the subjectivity assumption that is underlying every theorem. This is in general quite a complicated task to characterize all these sets that make WQ surjective. Still, we can say quite a few things. For example, if you have two tuples of forms that have the same span, then they're also gonna have the same image. WQ is gonna have the same image. An example giving you a WQ which is surjective would be choice of monomials. You take all the standard monomials as tuple Q. At the same time, for example, if you miss one of the, if you take all the monomials and you miss one of them, which is this pure power, for example, then WQ is not surjective. At the same time, we can get an example where we get surjectivity even though Q doesn't consist of all the monomials, for example. This was suggested by somebody in the room here today. So now I would like to connect these Warring decompositions and decompositions on the rational variety to some other problems, such as the moment problem. First of all, I want to focus on decompositions over the real numbers now and positive decompositions. So when the weights are positive. And this is just because usually people study the moment problem over the reals and are interested in positive measures. Just as a small remark, you can see that given some form, then you can study the Warring decompositions of this form has a problem of decomposing the normalized tuple of coefficients of the form has the truncated moment sequence of an atomic measure. So this is what the line below. No, not again. Oh my god. I'm sorry. Okay. So the line below this is what exactly this is exactly what it's saying. That you see this is the normalized coefficient tuple, and we write it down as the moment sequence of the atomic measure given by evaluation at the psi i's and with the weight lambda I. So this is the connection that I want to use. And of course, the support of the Warring decomposition is also going to be the support of the atomic measure because the psi i's are the same. Now, I want to use this connection to get to quadrature formulas, which is a problem connected to the moment problem in general. When you look for quadrature formula, you have a measure, a Borel measure, and you wanna you take its moments, and you wanna find another atomic measure now, sharing the same moments as the first one, perhaps until some certain degree. And this is what we call the strength of the quadrature formula. just as an application of our result symmetric decompositions on the variety, we applied our results on the problem of quadrature formulas on a rational curve, which is somewhat of a not so recent topic, but recently there have been quite a few developments by Zala and Rina and Turati, for example. So this is where we applied it to, and this is the theorem that we got. So if you study a very special case, which is exactly the same studied by Rina and Turati, using completely different techniques about optimization, we're able to get some bounds on the number of items that your quadrature formula needs. In particular, you see that if our variety is just this rational curve given by this parameterization, then if we add the assumption on WQ, which is subjective, we can say something about quadrature formula for measures supported on the curve. In fact, the boundary we get is exactly traces back to the Gaussian quadrature formula in the even case, and in the odd strength case, we need an extra +1 term. This is the best that is possible to do. In fact, we proved that these bounds are sharp. This is also what the authors of the paper, as I said, Rina and Turati suspected, actually. Finally, we can somehow describe an algorithm to compute this effectively, explicitly these decompositions. This just implements the main theorem that I mentioned before. So you have some choice of Q and a q-symmetric tensor. Of course, you want to get a q-symmetric tensor, otherwise this is not going to have a q-symmetric decomposition, so a decomposition of the variety. And this is how you can actually compute the decomposition. And as also an advertisement for my Julia package, this is all implemented in the Julia software. This is you can find it at the end of the presentation. Just let me finish up this example because I also want to put under the spotlight another application of this work, which is about making the computation of Warren decompositions somehow easier. Because as I said at the beginning, this is quite a complicated task, but if our tensor has some extra structure, like it is a q-symmetric tensor, the job becomes much easier. So let's get back our previous example. What you can do, for example, is you try and use some known decomposition algorithms. For example, the one implemented in the TensorDeck Julia package. But unfortunately, this doesn't work. This doesn't work because the rank of this symmetric tensor that I choose is a bit too high. But the tensor is a q-symmetric one, so we can instead compute a q-symmetric decomposition of this using the algorithm that I just described. And we do end up getting a Warren decomposition, which is this one. But the main takeaway is that this is a way to exploit the extra structure that we have on our underlying tensor, especially with these problems of slightly too high of rank. Because what is actually going on here, you can think of it as you take your form, which is in the q-symmetric space, and you map it to a different space, which doesn't necessarily mean it has a bigger size, but the rank stays the same. The rank of the starting, the q-symmetric rank at the beginning, and the rank of the mapped polynomial, so what I was calling psi of p, is the same. And perhaps the rank of psi is not so large anymore in the ambient space. And this is exactly what is happening. So that's another application of this work, and this is it. Thank you very much for your attention. These are the references. other questions.
So for the quadrature formula that you have, what's the application? What can you integrate exactly with this formula?
For example, I mean, this is a theorem about existence. So if you give me like a moment sequence until some degree is not fully either two of the cases, and the proof is constructive, so it tells you exactly how to find such a quadrature formula so that you can make all the computations that you wish just by these evaluations at a point. So this is one way to implement.
Under which degree is your procedure effective?
It's not. It's a bit nuanced in the sense that it really that depends on the combination of the degrees, whether like how big the slice of rank that you gain. In the paper number 3, we have some graphs showcasing how you can increase the rank and gain some extra decomposition capabilities with respect to TensorDeck, the other package. So the difference is quite substantial depending on the size, because you need the rank to be smaller with respect to the number of monomials of half degree in the space with the z variables. That is the trick, the z variables.
Okay, there's no other question, then we thank again.